Bismillahirrahmanirrahim. Assalamu alaikum. I am Fakhr Lodi and this is our 36th lecture of Formal Methods for Software Engineering. We are discussing Z specifications and Z methodology in general. Remember that Z is a model-based specification language, and in this particular system of specifications, we define the system in terms of the state space of the system, and then we specify the behavior of the system, the dynamic behavior of the system, in terms of the changes in the state when a certain operation is performed. So what we do is we have small schemas. This is the strength of Z specifications, that we start with small schemas, or we can start with small schemas, and gradually we can keep on building complex specifications from small schemas. We saw an example of a telephone book in our previous lectures, where we started with a very simple telephone book, and then we added functionality, and then we strengthened that functionality using schema calculus and so on and so forth. So the idea really is that specify and build small components, and then use those small components to build further more complex specifications. Today we shall start with another example of Z specifications. From a specification point of view, there is not going to be much new in this specification, but this example illustrates a typical kind of a system for which Z is very useful. This specification is for an insulin pump. This insulin pump is used for patients with diabetes. So the idea really is that this pump is sort of put with implanted with the body, and it has certain functions that it performs. So it is it monitors the glucose level in a person's blood, and then depending upon the readings that it gets, it injects insulin into the blood, so that that blood sugar level remains at a stable state within the specified limits. Now this looks like a very simple kind of a thing, that is we need to have a monitoring device and then an injection. But the problem with this is, or the critical thing with insulin pump is that the insulin that is injected into a body, the amount of that insulin is very critical. If insulin is injected less than the required amount, the blood sugar level will rise, and then it creates some complications. Basically the idea really is that with this insulin pump, the blood sugar level is reduced to that normal range. But the other side is very dangerous also. That is, if more insulin is injected into the body than the required amount, this can cause death. It can be fatal. So you cannot have a software or a system in this particular case where you cannot afford to have a bug in this software. A bug will cause deaths, or it may cause deaths. So, you cannot play with the lives of people. So this is a typical example where Z or formal specifications for that matter are really very useful. The system itself is not very complicated. We have very complicated systems like cancer radiation machines, MRI machines, aircraft controls, nuclear reactor controls, and so on and so forth. Those are huge systems. This is, relatively speaking, a small system, yet it is very, very critical to have this system in sort of operation in a perfect manner, without any operational problems, without any defects. And hence, we are going to write or see Z specifications for this particular system. So let me show you a schematic diagram of this insulin pump, and we will talk about different pieces of this insulin pump, and then we will write the software that will control the operation of this insulin pump. We will write the specification of the software to control the operation of the insulin pump. So let us look at the schematics of this insulin pump. This insulin pump has an insulin reservoir in which we fill insulin, and this insulin will be taken from this reservoir and it will be injected into the body. It has a number of components. We have a needle assembly, we have a pump, we have a clock, we have an alarm, we have the controller, we have a sensor, and we have two displays, display 1 and display 2. So this is the basic schematic diagram of the insulin pump. Here the arrows, they show the flow of information, the direction of flow of information. So there is this flow from pump to the needle assembly, from clock to the controller, from controller to pump, from controller to alarm, from sensor to controller, from controller to display 1 and display 2. Now the first component that we have is the needle assembly. This needle assembly is connected to the pump, and this component is used to deliver insulin into the diabetic body. Then we have the sensor, which measures the level of glucose or sugar in the user's blood. The input from sensor is represented by some variable, and we will use this variable name reading ? in the formal specifications. Just a side comment here. Remember that when we use variables, when a variable is used for input, we put a question mark in front of the variable. When a variable is used for output, we put an exclamation mark at the end of the variable. So this reading ? this means that this is an input variable, and this will take the reading from the sensor and give this reading to the controller for the controller to take the desired or required action here. Then we have the pump. This pumps insulin from the reservoir to needle assembly, and the value is represented by the dose in the formal specification. Then we have the controller, which controls the entire system. It may have an on-off switch plus a button to set the amount to be delivered, how much insulin is to be delivered. Then we have the alarm, which goes off if there is some problem. The value is sent from the controller to the alarm, and that value is represented by this variable alarm and exclamation mark here. Then we have two displays. The first display, reading 1, first display displays the last measured blood sugar reading, and the other displays the status. We have the clock, which provides the controller with the current time. So these are the basic components of the insulin pump. The most important of these components obviously are the sensor that takes the reading and gives to the controller. Controller is where all the decisions are made, all the instructions are sent to different components. For example, it will take the reading from the sensor and then it may send the pump this instruction to inject a certain amount of insulin into the body, and it may send this message to different displays showing the readings, showing the status, and so on and so forth. So controller and the sensor, these are the critical parts, but the basic thing where everything is controlled, where the software resides, that is your controller. So we will write specifications for the operation of this controller, and then let's see what happens and how do we write the specifications. So once again, what we will do is we will define a schema for this insulin pump. There will be certain variables and there will be certain predicates, schema predicates and invariant conditions there. Once again, remember that the schema predicate is something that stays there forever. It does not change. And then we have predicates for all the operations. There may be a precondition, there are postconditions also, which basically tell us how does the state of the system change. That is, when we apply an operation, the operation may change the state of the system. These predicates, they tell us what is going to happen. And for each operation, we may want to write a separate schema that will give us all that information. So this is all that we have discussed in the previous lectures. So, there is nothing new that I'm telling you here. So we go and discuss now the specification of the insulin pump. In the insulin pump, what we will have to do is we will have to take the reading from the sensor. Based upon the reading, we need to calculate the dose that need to be injected into the body. That is the insulin that needs to be injected into the body. And it will depend upon certain parameters that are set, and those parameters may change from a patient to patient, but in this particular case, we are going to keep those parameters kind of constant, at least for the time being. Then there are certain displays, certain things that need to be displayed onto different displays. Everything will be done and controlled by our controller in the insulin pump. So let us go back to the slide and look at the schema for the insulin pump. So this is the schema for the insulin pump. We have the first variable reading question mark, which is of type n, natural number. Dose and cumulative dose, again natural numbers. So we have two variables, dose and cumulative dose. Then I have three readings, R0, R1 and R2. Then I have the capacity. This is the capacity of my insulin reservoir. I have this alarm, which is going to be an output variable. It is going to be either on or off. I have this pump, which actually sends this insulin to the needle assembly. Once again, this is an output variable from that point of view, and this is once again of type natural numbers. And we have two output variables, display1 and display2, which are of type strings. Then I have my schema predicates. The first predicate is dose is less than equal to the capacity, and dose is less than or equal to 5, and cumulative dose is less than or equal to 50. Now this first predicate, what is it saying? It is saying the first thing is that this dose cannot be more than the capacity. And capacity is, to start with, what was the maximum capacity, but it means the current value of the capacity will be equal to the insulin left in the reservoir. So you cannot have a dose which is more than the insulin which is left in the reservoir. अगर मैं कहता हूं कि the patient needs 5 units and I only have 3 units, obviously nothing should happen. There should be a problem. There should be some kind of an alarm. This predicate cannot fire, and hence we have a problem here. This is an invariant condition. Second part of the predicate is that this dose that we will calculate and will inject into the body will not exceed 5 units. So it will be less than or equal to 5 units. And remember, it is a natural number, so it cannot be a negative number also. The third part of this predicate is the cumulative dose is less than or equal to 50 units. Now, what is this cumulative dose? This cumulative dose means that the dose or insulin injected into the body during a fixed period of time. For example, we can say cumulative dose in the last 3 hours, in the last 10 hours, or whatever. जो भी हमारी रिक्वायरमेंट होगी, जिस तरीके से भी हम इसको डिफाइन करेंगे, for that period, what is the cumulative dose? How much insulin has been injected? And when we calculate things, when we calculate dose, this cumulative dose cannot exceed that upper bound. So ये हमारे पास पहला predicate आ गया. The second predicate is capacity is greater than equal to 40 implies display is equal to this null string. Capacity is less than equal to 39 and capacity is greater than equal to 10 implies display is equal to insulin low. Capacity less than equal to 9 implies alarm is equal to on and display is equal to insulin very low. Now we have these 3 predicates, although these were 3 separate predicates, but I read them simultaneously as one, although these are 3 different predicates. Here what we are saying is, if the number of units present in the reservoir are more than 40, we are okay. We do not need to add more insulin to the reservoir. It is still good enough. But as soon as it becomes less than 40, between 39 and 10, both inclusive, we will display this message. This is kind of the status that we have, that insulin is low. That is, we need to refill the reservoir. and if it falls below 10, then we are not going to change the message. We are not just going to do that. We are going to now say that insulin is very low, but at the same time we are going to have this alarm off, so that there is this kind of alarming signal that the user gets and knows that there is something wrong. And in that particular case, we say that insulin is getting very low, it must be refilled. Remember that the maximum dose that we give to a patient at one time is 5 units according to this schema. And if it goes below, let's say 5, and that is the amount that we need to give to the patient, obviously that amount cannot be injected because it will violate the first predicate. So unless we add more insulin to the reservoir, nothing will be injected into the body, and that means the sugar level will shoot up. So we have a problem there. So but this set of predicates, it makes sure that some kind of information is sent to the user so that the corrective measure can be taken. The last predicate is R2 is equal to reading ? This basically says that the latest reading of the sensor is stored in this variable R2. So we have this set of predicates. So the first part of the schema, as we already know, those were the state variables that define the state space. The first predicate is the schema invariant, and then display 1 shows the status of the insulin reservoir, and so on and so forth. Now let us look at the dosage computation. Now this schema, which is dosage, we say it is delta insulin pump. Remember, when we use this delta in front of the schema name, which has already been defined, that means this schema will change the state of the state variables that are used in the previous schema. So this operation is going to change the state of the previous schema. Now we calculate the dose by comparing the current reading with the previous 2 readings. The current reading is R2 that we saw in the previous predicate, the last predicate of the previous schema, in which we said R2 is equal to reading. So that is the current reading or the current value that we get from the sensor. The previous 2 readings are going to be R0 and R1, and I'm going to show you how do we get R0 and R1. Then we have this dose, which is calculated to be either it is 0 units, it is 0 unit, that is insulin is not going to be delivered, there is no insulin to be injected, if the rate of change is decreasing. So that means that insulin is going to be delivered only if the rate of change is not decreasing. And how do we look at the rate of the change? We say R1 is greater than equal to R0. So R0 is the first reading, R1 is the second reading, and R2 is the current reading. So if we look at the 3 readings, the most recent is R2 and the oldest one is R0. And like I said, that I will talk about from where we get the values of R0 and R1, that I will show you in a minute. So R1 is greater than equal to R0 and R2 is equal to R1. When R2 is equal to R1, that means the current reading and the previous reading, they were equal. So there was no change in the status, in the reading, in the blood sugar level. And R1 was greater or equal to R0. Or R1 is greater than R0 and R2 is less than R1. Now what does that mean? It means, when we took the previous reading, that previous reading goes into variable R1. R1 was greater than R0. We probably injected some insulin or whatever. And now we have taken the current reading, and current reading says that R2 is less than or equal to R1. That means there is a slight change. It is going, the blood sugar level is going down now. Or R1 is less than R0. So previous reading was less than the reading before that, and R1 minus R2 is greater than R0 minus R1. So R1 minus R2 is greater than R0 minus R1. So we are comparing the change between two subsequent readings, R1 and R2 and R0 and R1. If the difference is between R1 and R2 is greater than the difference between R0 and R1, then we are not going to, give any insulin to the patient. The dose is going to be 4, and so that was the first part of the dose calculation. That is, dose is equal to 0 and the entire predicate, or dose is equal to 4, and now we have another set of equations which tell us, when are we going to give 4 units to the patient. Finally, we have dose as calculated as equal to 4 multiplied by R2 minus R1, and then we have another set of logical statements. So यहाँ पर मैंने आपको exact उसका मतलब क्या है, I mean, I did not go into that dose calculation because this is something which is outside our domain. An expert would have told the specifier, okay, this is what needs to be done, and this is when we give 0 units, this is when we give 4 units, and this is when we give units other than 4. It has to be less than 5, but it could be anywhere between 0 and 5. So those predicates that we saw, those gave different conditions for calculating the dosage that is to be injected into the body. So there are 3 possible things: 0, 4, or something between 0 and 5. Now let us go back onto the slide and look at the rest of the predicates. Then we see the second part is, after the dose has been calculated, we update the state variables. The new value of capacity, that is capacity prime dash, is equal to capacity minus dose. Now this is a straightforward trivial thing. Remember that when we make a change to a variable, we put a small hyphen at the end of the variable, which means that this is the new value of the variable. The old value would be the name of the variable itself. When we use the name of the variable, that means that is the value of the variable before the operation, and with this small hyphen, this is the value of the variable after the operation. So here, very simple thing, we are saying that, dose has been calculated and the capacity will be reduced by that amount. That is, if previously we had 45 units and the dose is to be calculated, dose was calculated to be equal to 3 units, then we do this 45 minus 3, so new capacity would be 42 units. So this is a very straightforward, simple thing. The cumulative dose, the new value is equal to the old value of the cumulative dose plus the dose. Once again, a straightforward calculation, nothing very difficult to see, it's trivial. That is, we are calculating the cumulative dose that has been injected, the cumulative amount of insulin that has been injected into the patient, and this new value is added to the old value, and then we get the new cumulative value. And finally, we have the new value of R0 is equal to R1, and new value of R1 is equal to R2. Now this is where we are giving our variables new values. We are updating the readings. Remember, the current reading is R2. We have used this current reading in dose calculation. Next time we take the reading from the sensor, that reading will go into this variable R2. So when we calculate the dose, at that point in time, what we do is we update the values of R0 and R1. So R0 gets the old value of R1 and R1 gets the old value of R2, or R1 gets the value R2. Now the next time I get R2 from the sensor, the new reading, the previous two readings would have been stored in R1 and R0, just like we have shown here. Note one thing here, that these are not assignment statements. These are logical expressions. All of these are logical expressions. The right hand side is equal to the left hand side. So it is not the same variable which is appearing on the both sides of the this equal sign. If the same variable appears on both sides of the equal sign, then usually that is not a legal logical expression. I cannot say A is equal to A plus 1 because that is an incorrect logical expression. Here I'm saying is, when I want to say this thing, I say this A, now A has this new value A prime. So these are logical expressions and not assignment statements. These are predicates. So please remember this. You must also remember that the invariant is always applicable. There is no need to repeat it again. Then there are some output schemas. The output schemas model the system displays and the alarm that indicates some potentially dangerous conditions. The output displays show the dosage computed and a warning message, and the alarm is activated if blood sugar is very low. This indicates that the user should eat something to increase their blood sugar level. Now here we have two things. I've talked about this alarm which says that the blood sugar level is very low, and it is an indication to the patient that the patient should take some sugar. We were using the same alarm to indicate that there is less amount of insulin left in the reservoir, so that reservoir needs to be refilled. So we have the same alarm signal. So since it is an output from the device to the user, so this is an output variable. It may be used in two different situations. And how do we know what action is to be taken? That will be the display. So the display will guide us. There is alarm, the display may show that we have low insulin in the reservoir. And we have alarm, the display may show that the blood glucose level of the patient is very low. Now the patient is supposed to eat something. So this is something, please keep this in mind. I'll come back to this and then discuss it, because this may create some kind of a problem later on. But once again, remember that we have this alarm situation which tells us what is going to happen. Now we have this output schema, display. Display updates insulin pump, and the predicates are display 2, which is the output variable. The new value is equal to converting this dose to a string, natural number. Dose was a natural number, so converting this natural number to a string and displaying it on display 2. And reading is less than 3 means, that is, it implies that display 1 will get this message that sugar is low. Reading, which is greater than 30, will display or will put this message sugar high on display 1. Or reading greater than equal to 3 and reading less than equal to 30, that is between these two values, we will get the value or display on the display 1 is equal to OK. Now this, remember that this reading is, we are getting this reading from the sensor. This is the reading of the blood sugar level. So we say that if the sugar level is less than 3, that means sugar is too low. If the sugar level is greater than 30, that means sugar is very high. And if the sugar level is between 3 and 30, it is within normal range. And the display, that is display 1, will display the message accordingly. So whatever the value, a proper message which sort of translates that value into something that can be easily understood by the user, is displayed on the display. Then we have the alarm. The alarm schema once again updates the insulin pump, and it is that reading is less than 3 or reading is greater than 30, alarm is on. Reading is greater than equal to 3 and reading is less than equal to 30, alarm is off. Now this means, alarm on and off means that, when we say the alarm is on, that means if it is a buzzer, it will sound. When we say alarm is off, that means there will be no sound. But it could be something else also. So what we are saying here is that, not only does it display something onto the display unit, but depending upon the situation, if it is, less than 3 or greater than 30, less than 3 low sugar, greater than 30 high sugar, in both cases we will set it to be equal to true or on, and if it is kind of a buzzer, then this, so we have this audio signal to the user so that the user is alarmed of the situation. Once again, there is nothing very special about this predicate, but it shows how can we build more complex system from small predicates. But this will also translate into some kind of a problem that we have to talk about. We will discuss very shortly. But for the time being, let's go back onto the slide. Schema consistency is one of the most important aspects. It is important that schemas are consistent. Inconsistency suggests a problem with the system requirements. When we write these specifications, what we need to have is we need to have consistent schemas. What does that mean? It means that these schemas, they should not contradict each other. They are all related. And it should not be the case that in the one case, one schema is saying one thing and the other schema is saying something else. So this inconsistency is something that first of all needs to be identified, if there is any, and then it needs to be fixed, because that means the requirement was not consistent, it was not written properly. And if it was not written properly, obviously if we try to build a system based upon that, that will cause problems. So the first thing that we need to do is we need to check schema's consistency, and we have tools to do that. For the time being, we are not going to go and discuss those kind of tools, but I'm going to show in this particular example where did our schemas go inconsistent, where were they inconsistent. So let us go back and try to look at what happens here. We have the insulin pump schema and the display. The insulin pump schema has certain display, and it displays insulin low, insulin very low, or nothing, depending upon, basically it is showing the status of the insulin level in the reservoir. The display schema, on the other hand, is showing the sugar level in the blood of the patient, whether it is okay, very low, or high. Now, note in this particular case that in both these cases, the output is displayed on display 1. Now, the question really is, which message should it display? Should we display a warning message about the insulin reservoir, or should it display the state of the blood sugar? And note one thing here, that we have a problem here. Since we have only one display where the alarm message is going to be displayed or the status is going to be displayed, we have to decide which particular message will be displayed. We may say, it all depends upon the situation. If it is an alarm, we should display which particular alarm will take precedence. If there are more than one alarms or more than one alarming conditions, that is, let's assume that the insulin in the reservoir is low, that is an alarming situation, and at the same time the blood sugar level in a patient's blood is high. In both these cases, there is this alarm. The alarm signal will be set to on. It will sound. The buzzer will be turned on. But which message is to be displayed? So we have to specify the priority, maybe. Or we may have to sort of display both these messages one after the other, maybe kind of rotating. but we have to sort of resolve this situation. In the current situation, I am not very sure which message will be displayed. Am I going to display OK message, or am I going to display nothing on the display if my reservoir is full and the patient sugar level is between the specified amount? So I have a problem here, and I have to fix this problem before I can move further. So this is something that I need to check. This is something that there are tools that will help me in checking and telling me that here we have some inconsistency problems. So as I said earlier, that this must be resolved before implementation of the system can start. So in this example, what we have seen is actually nothing really new from the previous examples, but a very important concept has been introduced here. And that important concept is the question of consistency. That is, when we write the specifications, they must be consistent. And if the specifications are not consistent, that means they will conflict with one another. When there is this conflict, that means we are going to have problems in the implementation. And when there are problems in the implementation, that means we have, a situation where we don't know what to do. In our systems where software, the accuracy of software is required, we cannot have defects in the software. It is of utmost importance that we pay attention to these kind of problems. We cannot have a situation where we have inconsistent requirements, resulting in conflicting situation and resulting in maybe malfunctioning or maybe giving inconsistent messages or incorrect messages to the user. On the one hand, I may be having an alarm situation, and on the other hand, I may be saying on the display, it is okay. My alarm is turned on because the blood sugar level of the patient is very low, but my display is showing okay or nothing because it is showing that part of the display, or it is taking a instruction from the reservoir, from the controller, and showing the reservoir related message. So these kind of things, they need attention and they need to be properly handled and fixed. Now, this example, we will be talking about this consistency in more detail. In the next lecture, I will go back and talk about some new fundamental concepts. And those fundamental concepts, they deal with how to take these specifications. First of all, I have already talked about the consistency, but there is another very important aspect, that is, we have to actually implement these specifications at some point in time, convert them into executable code. So what are the steps that we need to take that will take us from the specification to the coding and implementation part? So in the next lecture, like I mentioned, we will take a step further from specification to implementation. Note one thing here, that the implementation actually is another form of specification. ये शायद बात मैंने बिल्कुल शुरू में भी की थी कि every statement, line of code that you write in your program, that is some sort of specification because it has a very precise meaning. But since it is, relatively speaking, written at a lower level of abstraction, the overall picture is lost. It is difficult to extract the overall picture. So when we work at a high level of abstraction, like writing specifications in these different formal languages using Hoare logic, or design by contract, or Z specification, or so on and so forth. So our discussion is at a very high level of abstraction. So the information, it is easier to extract the information from that. In this particular case, we go low, we keep on refining this situation, and then we will ultimately reach a point where this can be compiled and executed. So we shall start discussing that from the next lecture. Till that time, Khuda Hafiz or Assalamu Alaikum.